we can start, right? Okay, okay, so can I wait for the second lecture? Yeah, and today we'll be talking about memory signals.
Okay, so last time I had given a basic introduction to GR, in which I had said that GR is geometry in the sense that it's a coordinate transformation between a rest frame which we will always have, which is called which is guaranteed by the equivalence principle, which tells you that around any particle, which is you can always choose a frame where the gravity disappears locally. Okay, and the second principle we used was that this interval, which is mu nu and other things which are scalar like this. So this I defined in terms of the this is invariant. So using these two, you can start from your equation of motion. So this, let's say, square equals 0 in the rest frame or in the frame where there is no gravity, and make a coordinate transformation. So make a coordinate transformation from this frame to any other frame, like the frame fixed to the earth, let's say, or any other body. And when you transform these equations, you will come across various structures. For instance, you will get this geodesic equation. So this was so this was x mu plus so we introduced this, which actually was just coming from the coordinate transformation, and also then we wrote the geodesic deviation equation, in which we had a quantity called, so this is the Riemann tensor. Okay. So, and this again was written in terms of the coordinate transformation between the rest frame and this, and G mu nu itself is defined in terms of this coordinate transformation. So all the structures of GR are actually coming from, you can derive from this equivalence principle and the fact that you have some interval which is invariant under a transformation. Okay. Now today I am going to do a different perspective. So this is GR as field theory. Okay. And one thing different I'm going to do from last time is that I'll give you the main steps, but I'll skip the algebra because that takes too long and then I get slowed down, I don't cover what I intend to cover. But if you want the complete algebra, you can contact me, you can have it here in the notes. So you can take pictures. If some steps you don't understand, you can take a picture and of my notes and then follow it at your leisure. Okay. So here in this picture we start with an action. Okay. So we write the Einstein-Hilbert action, which is so R comes after you contract all the indices using G. So that's called the Ricci scalar. And this This is the gravitational constant. This is 1 upon m Planck square. This is 1 point. And notice that this comes in the denominator in the Einstein-Hilbert action. Okay. So, in addition, you have matter, and the action is that will involve the metric as well as fields and their derivatives. Okay. So you have to basically, when you're writing this metric, this action, start with the, let's say, okay. So this is in the rest frame. And you can write your whole usual action that you used in the Minkowski space. Then make a coordinate transformation, which means that basically this would have been eta mu nu d mu phi d nu phi. When you make a coordinate transformation, this will go to g mu nu. So this is the covariant okay. So what this means is the equivalence principle tells you that starting with this, you can choose a frame where this eta mu nu is 0 and so sorry, g mu nu goes to eta mu nu. So this is the rest frame or inertial frame, let's say. But r mu nu will go to some other r prime alpha. This will transform like a tensor, but this does not necessarily vanish. Okay? Neither does r mu nu or r. These don't necessarily vanish. Which means that when you're writing the action, if you include terms like, so you can write a covariant term like r phi square, for instance. Okay? But this will violate the equivalence principle because you can always, this will not go to a 0 in your rest frame. Okay? So you can of course have that, but this goes beyond Einstein's theory if you have this kind of terms. Einstein's theory will not allow you, even if it's a covariant term, you cannot write that in the Lagrangian. Okay. So that's the, so for instance your f mu nu, so this will be the Lagrangian for your electromagnetic field, where this is contracted with G's and f mu nu itself is basically d mu a nu. Here if you can start by saying that okay, let me replace it with a covariant derivative in each place, but you'll see that the covariant derivatives cancel and you'll go back to this. And again, if you write terms like r mu nu, f mu nu, etc., these violate the equivalence principle, so you don't include that. Okay. So in general, you can write a Lagrangian in the curved metric and okay. So now what we do is vary SCH plus the matter and the gravity Lagrangian with respect to the metric. Okay. And the usual way we try to minimize this action with respect to this variation in a field. So when we do that, again I'll skip the steps and you can copy it from me later, from my notes later, that the action okay, this will give you so I'll erase this. And the variation of the matter with respect to the metric, this gives you something which you are familiar with, which is so I'll write this, let me write a little more detail. Times delta, I think this should have been L. Okay. So this term, so the action has a root G times L. First you vary L, and then when you vary root G, you will get that term, and the total is this. And this is something we call the stress tensor. So this is defined as the stress tensor. So this is T mu nu of whatever is the field. Okay. So the total action then is so this actually involves a lot of algebras which I have skipped, but you can look it up in various books. So one book which I recommend for this Lagrangian thing is Z. Gravity in a nutshell. Okay. Where you will see, you can check all these. Okay. Now we'll get to what's called linearized gravity. So in linearized gravity, we start with this so we expand the field around the flat metric. Okay. So this is not going to a particular frame, that is, this is for any frame. You can expand it around as a flat metric plus an extra term. Okay. And don't go beyond that in any expression. Okay. And you will raise and lower indices using eta mu nu in various expressions if there is already an h mu nu present. Okay. So this is the breakup when you treat this as your metric, or this is the thing that this is the what causes the strain in the length scale. So this is the proper metric which is dimensionless. But if you want to write a field theory, then you treat it like a quantum field. So we are talking about emission and absorption and so on. Then so this is the gravitational wave So we want to measure the gravitational wave. This is the way you split it. If you want to treat it as a field, then since it's a quadratic, it will turn out that the field will be of this nature, h mu nu. So this will be the Lagrangian, and this is the second derivative term, which means that this should have dimension 1. So mass dimension, okay, to get a canonical dimension for the Lagrangian, for the kinetic term. So then we split it as eta mu nu plus a thing which has a inverse mass. So this will be kappa h mu nu, and here kappa will 32 pi g. Okay, and the reason this is chosen is as this number is that you can calculated an elementary amplitude where you have exchange of a graviton, and this should give you your Newton's law. So this in position space should give you, what is that? Something like that. So that matching, so supposing this is kappa by 2 here and kappa by 2 here, then in the Lagrangian it will be kappa by 2 in the interaction. So then when you want to match this potential with your usual Newton's potential, you have to choose kappa of this. Okay. Now in the linearized version of gravity, so gravity was the symmetry was that there is an invariance under a general transformation of x mu going to any other coordinate. So here it will be x mu going to whereas earlier it would have been like x mu goes to any function of. So this is the general coordinate transformation, and this is the linearized version. And then your h mu nu will go as h mu nu plus so under this transformation all your Lagrangian and action and interaction has to be a symmetry under this transformation. So this is what goes, this is a gauge symmetry for this linearized theory. Yeah. So, no, kappa remains kappa. V gravity limit is taking a linear order here. If you want higher order terms in, supposing h mu nu is large, the strain is actually not small, not less than 1. Here you are assuming that h mu nu is less than 1. Yeah, so I am keeping linear order, then there will be kappa square, h mu nu square and so on. So I am expanding around this. Yeah. Okay, so M1, very good. So I will actually calculate this later, but what you will see is that this is a T mu nu which will couple to a, so the T mu nu here contains the M1. T mu nu here contains the M2, and there is a coupling between the T mu nu and the H mu nu. When you exchange the H mu nu, then it will be just T mu nu of this side and T mu nu of that side. So that's your, but I will do these things little later. Okay, so again skipping a lot of steps, if you start with Einstein's equation, which I had, did I write the Einstein's equation? No. I forgot. So, right. So I had written that the total variation of this plus that would give you minus r mu nu. Sorry. And that's your, you can write it in any, if you take this to the other side, it is, so this is the usual starting point for our general GR, but this can be derived using a Lagrangian here. And now if I use linearized gravity, okay, starting from here, what I get is this side goes to minus half of h mu nu minus this is what, okay. I think this should be a this, when it went to the other side, this should have been a minus. Okay. So, and in going from here to here, I have chosen a so I've used this freedom to redefine my h mu nu by choosing a gauge. So this is what's called the Didonder gauge. Basically, okay, and this quantity is basically, it's defined as and so this gauge condition, so this is the Didonder gauge condition. So I again emphasize there's a lot of algebra from going from here to there and so on, so you can look it up in the books or you can. Okay, I'll write one more step here if you want. No, I have linearized that I can write, give you one or two steps or you can see what's happening. I mean, it's okay, so calling this G mu nu, the Einstein tensor is Okay. So this, if I write it in the linearized term, so in the first order what I will get is, this is minus half box h mu nu bar So this will reduce to that times, I think there is a, yeah. So this will reduce to that, and then I take, you can see that remaining are, if I take a D row, any of these, this gauge condition, then all these other terms vanish. And I'm left with that. Okay. But again, from here to here also you have to write all of these in terms of the linearized this thing and get it. So then this gauge simplifies by taking out a lot of terms. Okay. Yeah, so you can copy take the notes from me and fill it up yourself. I mean, try to derive it. Okay, so in general then, so your Einstein's equation then is this is a linearized. Okay. And the corresponding Lagrangian will be for the gravity part. So that when you take the first derivative variation with respect to h bar mu nu, you will get this one. Okay, which means you basically write the r term, it's actually bilinear in this. Okay, so this is the gauge fixed Lagrangian. Otherwise it will contain all those other terms. If I expand the Lagrangian, it will contain all those terms, then I gauge fix it by removing all those. Okay. Now, so h mu nu is 4 by 4 symmetric matrix, which means it has 10 independent components. And you had 4 functions to remove degrees of freedom from here. So this is 10 minus 4, 6 degrees of freedom. So for instance, if you xi mu nu, so this is this one, this function if you choose, okay, so from h mu nu that takes care of 4 degrees of freedom by choosing this function with 4 components. Okay, now so in general, which is if you have a off shell graviton, this will have all these components. But if you have an on-shell graviton, what does on-shell graviton mean? So here classically on-shell will mean that it obeys this condition. Okay. So it's propagating without the source, it's propagating through the free space. So on-shell graviton then has, if you take this, this is coming after the gauge fixing, okay? But in addition, you can choose a gauge, h v nu goes to something like, again the same. And choose this such that it is a harmonic function. So this. So this you couldn't do, okay. If you do that, then you can change this by making this transformation with the harmonic function and still remove some degrees of freedom here. Okay. So then so for a propagating graviton, so there are 6 minus 4 coming from choice of these harmonic functions, 2 degrees of freedom. Okay. And so this is 2 degrees of freedom are only if you have a proper graviton propagating in free space. If you have a source and you have a off-shell graviton, then you have other degrees of freedom. Okay. So, yeah.
So that first 4 that is minus.
This is different from this. So this first 4, this one, which first one? No, sorry, I ask your question again.
Yeah, so the first 10 minus 4 that is minus.
Yeah, those are to simplify this equation.
Yeah, you told that it was a choice of xi.
Yeah, by choosing a xi mu, you can choose a xi mu such that del mu of this is 0.
The second term is 0.
Yeah.
So that will give.
Not the second term. Del mu of h bar mu nu. This is 0. That's your gauge condition. So that is 4 equations. It has another, that h part. So after having made that choice, you can choose again. When you have this equation, the free space equation, you can still change this h mu nu by adding a harmonic function like this. Now, this will only work if the right hand side, the source is not there. Supposing the source is there, then of course, you cannot add a function because it will depend upon what is the source. So it will be a general thing.
So then I'm confused, right? So suppose I am very near to a source.
Yeah.
Then I will not get a master's level.
You will, yeah, if you have the Newton's potential, it is not this one. But if you have a gravitational wave, it is this one. So we are very near the source, then you are using this equation. So box, no, it is applicable.
So if you are, but even if the source has mass,
Huh?
but I mean generally speaking, if the extent to which it is, when you have a gravitational detector or something like that, the assumption is that it is largely doesn't matter. Like the medium is not really.
No, I'm not talking just theoretically, not theoretically. How close do I have to be near a say module to see this?
Okay, so this is a general equation, right? So basically your h mu nu will be your Green's function, which goes as 1 upon r t mu nu, right? So this is in general both the wave as well as your phi, the Newtonian potential, will fall off like 1 by r. Okay, so that remains the same. But when you go far away, the longitudinal degree of freedom will not propagate. So this, as it turns out, when you obey the time, this thing, that phi will be time independent.
In principle, if there is a medium, does the number of delay count changes?
What?
Plasma frequency.
So if there is, in principle, if there is a medium, does the number of degrees of graviton change?
Yeah.
But I think even there,
Yes.
it changes
Oh.
because you can probably define a psi prime nu which is a solution to the source equation. I think you might be able to even there.
No, it changes. So
That or maybe this is equivalent to the plasma frequency of
yes,
Yes, that's
it is equivalent to, so you will have a longitudinal graviton
Yeah.
which will have a propagating longitudinal graviton. Here the longitudinal mode does not propagate, but if you have a medium, the longitudinal mode also propagates, the scalar mode also propagates.
So this is the analog of, in electromagnetism, 4 minus 1 minus 1 is 2. Here it is 10 minus 4 minus 4 is 2.
Correct, exactly. So electromagnetism also, after using your gauge condition, you can remove from 4 to 3, and from 3 to 1, you have to use this harmonic.
The reason we don't observe this in photons, we observe this because it's electromagnetic. When I'm
No.
doing the
No, no, gravitation.
in the plasma frequency it has to be electromagnetic by definition.
Yeah, so
And here it's 1 over g square or whatever. G Planck, 1 over n Planck.
Yeah.
That's why it's so called plasma frequency.
Yeah, and there is some.
What is the analog of plasma frequency? What is the analog of physics? So there is a.
So normally you see, if you have a collections in gravity, if you have a collection of dust, that means non-relativistic particle. When a gravitational wave passes through it, the refractive index is still 1. Okay, that's a rigorous derivation. So only if there is a pressure in the T mu nu, you will have a refractive index, and then you will have this analog of. So dark matter, for instance, is
So you have it in self-inflected duct, that's what you write.
possibly like you should have some for instance, the most famous case is viscosity. If there is a viscosity, then it will affect the propagation of. But pressureless matter does not affect the gravitational waves. So which is why.
Is there a simple way to see that, like in the sense of like in electromagnetism, how is the
No, in electromagnetism is always a plasma.
There is always that. So
But here it's a special this thing.
so how is there a simple way to see?
No, there is no simple way, but I can. There is.
But you're sure that there is no simple way?
Well, I have actually looked. There is no simple way. Depends upon what you mean by simple. Okay, if you have come this far, maybe you can, it is simple then. So I was trying to recall who's, one of the authors is my colleague Prasanna, and I think Ehlers, Prasanna plus one. So there is a very well-known paper which proves this, that any matter, no matter what the density, like if the gravitational wave moves through Earth, it does not slow down. Okay.
But there is photon pressure. Maybe it's not observable.
Photon pressure, neutrino pressure, photon, those, relativistic particles will do that. Yes, that's correct. Which is why for the dark matter question it is not relevant, but it's an interesting thing to probe. That what's the observable signature of this refractive index. Okay. So now we will just okay, so now we are going to, we have this h mu nu, and we have only so this gauge choice, which we had selected, ensures that del 0 h00 is 0. That means this is the Newtonian potential. That is a constant. That does not vary in time. And h0i is 0. And hij is transverse and traceless. Which means that supposing I have this is 0 and where Ni is the direction, sorry, so that is the same thing, eta ij. So this also can be written as Ni. So it is transverse to the direction it is propagating, and also it is traceless. So for instance, if you have a propagation, choose along z axis. So whichever axis it is propagating along, you choose that as your z axis. Then your hij, ij are 1, 2, 3, or I can is h plus so this is traceless and it is transverse. So the components are transverse to the z axis. There is no component, there is no z, I z is 0. Okay. So these gauge conditions force this on you. So in general, when you have a general direction, which is what we will encounter, we have to put some projection operators to get the physical graviton. So yeah.
The zeroth derivative is 0, but in principle h00 can be non-zero.
Yes, h00 can be non-zero, but this does not propagate. Okay, so this is a question he was asking, that h00 is a Newtonian potential that falls off 1 by r, but it does not propagate. Okay. Okay.
As long as matter is pressureless, one can still stay do that even when that's not.
Yes, as long as matter is pressureless, all this holds because the refractive index of gravitons is 0 in non-relativistic matter. Then look up at that paper. Okay, so we have projection operators. We define projection operators. So these are, so Pij, n being the direction in which the graviton is.
So pressureless means, so dark energy is pressureless. How did
Dark energy can affect.
it was defined as?
Yeah, that has pressure, negative pressure.
Yeah, that's it.
Yeah. Okay, and you can see that Ni dot this will give you 0. Okay, so this projects Ni dot Pij 0, and if you want, there is another operator as Ij Kl, which I will define as then any index contracted with this, from with any of these indices will give you 0. Okay. So what that means is that if you have a 2-indexed object, let's say Hij, and you operated with lambda I, j, kl, so let's make this kl and define this object as Hij, tt. Okay, this kl. then this object is transverse and traceless because of the properties of this. Okay. So that's what normally we do, that we calculate Hij and then we have to put a projection operator to get the traceless transverse component out of that. Okay. All right. So now we solve this equation, and this is where I'll.
You can erase this part if you don't
Huh?
mind. You can erase this part if you don't mind.
Ah, okay. You want me to? You?
Yeah.
Yeah. All right. Okay. Okay, so now I will tell you the generation of gravitational waves. So the first part is from slow objects, which gives you the usual quadrupole formula, and so that works for most of the things which we see, binary. But if you have sources which are relativistic, then you'll get the memory signal. So then GW from sources.
DC memory signal.
What?
This is the DC memory signal, the permanent shift.
Yeah, DC memories. That's and if you want the TT version, you have to apply a lambda ijk on this. So normally you will write it. Okay. So this is x and t. This lambda will actually depend upon n, which actually is the direction of the graviton, which is n is x by x. So that depends upon the direction of the graviton here, where so to solve this, we start with the Green's function. So we can, apart from this projector operator, we can use the scalar Green function. So we can start with and I'll assume that you have all seen it. This is the scalar function, and this is solved by minus 1 upon 4 pi So actually you can start with a more covariant form, but then it reduces to this form. Okay. So this is the Green's function for the box operator in 4 dimensions. Okay. And so our Hij Tt of x and t will be so h at xt will be Green's function convoluted with this scale, okay, of the stress tensor in the x prime t prime coordinates. Okay, and if you now this n is independent of x prime, so that can be taken out and you can write it is a I think the first equation should have had a minus sign here, sorry. So this is and the Green's function has a minus sign, so the overall there is a plus sign. So the 16 pi g divided by 4 pi, that gives you just 4g. Okay. Then this lambda I j k l. Okay. So first you can do the integration over this t prime. Okay. So this is d for x prime. Okay. And this Green's function, and this will give you 1 upon x minus x prime. And if you do the integral over t prime, what you will get is and t prime here will be replaced by t minus okay. So this t prime got replaced by this object. Right? All right. So I guess I can remove this part. Okay. So now first we deal with slow objects and distant. So slow objects means your x prime by t prime. Okay. The source velocity is small. You can drop those terms. And distant means that so x is the distance to the observer. This is the extent of the source. So source is confined compared to the distance to the object. So the picture is something like that. You have origin. This is x, observer, and any point here is x prime, and this is x prime. And you have to integrate over all x prime where the source extends. All right. So if you do that, so you can expand where n is again the direction of the source, which is the direction in which the graviton propagates. Plus order and I'll call this so you can simplify like that and just keep the first term. So this will give you the quadrupole. If you keep the higher order terms, you'll get the octuple and so on. Okay. Also in the time, so you had this t of x prime tkl do the same in expansion in T and call this object T retarded. So I'll write it separately. T retarded is T minus R. So this thing over here becomes, if you take out T retarded, this is 1 plus x prime mod divided by T retarded dot n. Sorry, this is x dot n. And this is the velocity of the source, sorry, x prime. Okay. So if it's a slow moving object, you can drop it, and if it's a relativistic object, you have to keep it and then do a different. So for slow sources, we can drop this. Okay. So in the end we are left with Hij xt equal to 4g by r lambda ij kl n. Okay. X prime and T retarded. We have dropped the x prime term in the time because of it's slow moving, and in the 1 by x minus x prime we kept only r because it's a distant object. Okay. So this is the general formula, and actually I personally, if you can use this straight away to calculate your Hij. So this will actually give you Hij tt, but conventionally instead of the stress tensor, people use the moment of inertia. So that is done by a little bit of convoluted method. So use the fact that d0, d mu, t mu nu is 0. Okay, component wise. So I'll not give you all the steps, but it's simple. Where the 0 here, or t, this is d0 is t retarded, which is t minus r. So you are taking derivatives with respect to retarded time because that is the functional form of which this TKL depend. And so I'll just give you what you get is, so using these, what you can get is TKL x prime T retarded is x . So this involves, so you can write this d0 in terms of dij. Okay. Expand this, for instance, you can write so take mu is equal to 0. So if mu is equal to 0, this will be 0 and equations of this sort. And you can then connect the ijk. So nu again you can take 0 or ijk, and you can connect this 0th component with this component, and by taking the time derivative or the space, you convert this into a space derivative and take integration by parts, because this is occurring in a volume, and when you integrate by parts you will get a surface, and if you go to a larger enough surface you can throw that term. Okay. So ultimately you get something of this and you can look up that it's a very trivial algebra, a few steps. And so finally what you get is,
that replacement should only be done inside the integral. Is that is,
yeah, this is true inside the integral. So and you can take d0 outside the integral because this is the time, and d cube x prime, this is xk xl I think this should be lower. The lower and upper doesn't matter in the spatial indices anyway. And this is what's called the moment of inertia. So this is the quadrupole formula. Calculate the moment of inertia in retarded time and take second derivative. That will give you your Hij. But in practice, for things like elementary particles, it's easier to just write. This works well for extended objects, but for elementary particles, it's simpler to write the Tijkl and use this. Gives you the same thing. Okay. Now I get to the, yeah. Why? So this is 2 object index. So it's a tensor. It's a 4x4. And then I choose any axis, calculate my moment of inertia. So I have my object here. I choose an axis and calculate my moment of inertia in that axis. Then I say that my observer is here at n. I calculate that moment of inertia, then put a projection operator. That will give me the components of Hij along the n. Okay. So I am free to choose any axis to calculate this. The axis I choose will also then change this projection operator. Okay. So in the end you will get the same. Okay. So now the more interesting case. So this is the formula which is used for calculating for binary sources and so on. But as I said, it's easier to use the field theory method, in which this is just an elementary process with the emission from a single vertex, and you get the answer directly in the momentum space, which is what is actually needed for comparing with experiments. Because what you need to know is, for any process, what is the power in the gravitational waves for a particular frequency. So it's better to calculate these things as a function of the frequency. Okay, now I'll go to, I have how much time?
0, 0 index is also in retarded time, right? This 0, 0 index in this slide like that. Is that correct?
Yeah, I guess. Yeah, the time here is now the retarded time. Yeah. So Xij is 0, 0. Oh, you're saying if you transform it to a.
No, I'm just asking.
Yeah.
Question, right? Is it T or T minus R? That's right.
It's T minus R. So it will matter if you are like, I have an object and I want to see this picture from inertial frame which is moving, then I have to transform this guy. And so, okay. All right. So now is the more interesting thing. What happens if you have fast moving objects?
Essentially, like an identical formula will also hold in the case of standard electromagnetism, right? I mean, it's so lower number of impulses.
Yeah. So there.
Electromagnetic. It's a very nice question. I don't think you should spend too much time into it.
No.
This is dipole radiation. Yeah.
No, this is actually not dipole radiation.
No, this is not. This is what the
No. So here the power radiated is 3 derivatives of your quadrupole, whereas in electromagnetism, so this is GW. So I'll show you how that comes. In a moment you'll see that. This is the power radiated. Here I'm calculating Hij. And this will be in EM. This will be d double dot, the dipole second derivative. Yeah, so here basically, okay, so the equivalent of here, this would be, I think when we do multipole expansion, yeah, also of non-propagating modes, like, you know, so this is equivalent of phi and A.
Phi what, sorry?
This is equivalent of phi and A, right, in the electromagnetism. So this will give you the dipole or the multipole expansion of these potential.
So is there some analog, you know, of, so here it looks like you have set phi to 0, the analog of that will be phi to 0.
Yeah, for propagating modes, again in photons phi you set phi to 0. Right, you choose your gauge conditions such that you have only true propagating, the photon has only the transverse modes. Okay. Okay, so now we are talking about relativistic sources. And this is something which is actually done in your master's class in electromagnetism. So basically this is what's called the Leonard-Weishart potential. So you can see that I am calculating things with a Green's function, and I am taking the scalar Green's function and then putting a projection operator. So that same procedure, if I do that, you will get the Green's function which you use, for instance, calculating the scalar potential of a moving source, which is this. So the derivation is the same. It's not similar, it's same. So I'll just show you what it is, and that's actually the memory term, which also exists in electromagnetism. So again, go back to this Hij Tt. This is 4G dt prime okay. I'll not bother about the projections, I can put that later. T prime okay, and now let's say talk about a moving point source. Then the stress tensor T mu nu is mass times the Lorentz factor times the velocity component. So this is T mu nu is defined as a field over all space time, but you have a source moving along a trajectory. So this is the trajectory of the source. Okay. So this defines, oh, here I can just keep it x for the moment. So this gives me the T mu nu, which is only non-zero at the source, but otherwise zero everywhere else. Okay, but it is a variable, and it's a fast-moving source, and Vs and are the usual velocities, and this is the gamma factor. And this is also the energy of the particle, gamma times. Okay, so I can erase this. So we again calculate the Green's function, which is so the Green's function now is 1 upon so x, and I'll write now x of t, or massless particles, it's actually p nu upon e. So I can you are talking about the trajectory.
I think there should be some affine parameters, yes.
Huh?
There will be some affine parameters.
Yeah. So this will be some affine parameter, but I think it's yeah. Yeah, it's, but there is a, so what I'll do is the end, I'll just translate the final formula into a massless particle without. So gamma Vs mu. Okay, I'll write the whole story here. So Hij, x and t will be my 4g times dt prime m gamma s Vs I Vs j, they should be written. Okay, times so what I have done here is I inserted that Green's function and integrated over x prime. When I integrated over x prime, because of this delta function, the x prime got replaced by x of the source. Okay, both there and here. Okay. Now we simplify this guy, and that's where all the work is. So delta of t minus so there is a t prime here and also the t prime in the source which is also moving. So you cannot neglect that dependence in t prime. So this I will again give you the basic steps. T retarded. So TR again is T minus R being x, the distance to the source, divided by all evaluated at t prime equal to t retarded. So you have a functional Green's function of a function. So you write it as Green's function of t minus r here, and you want this coordinate. So you have to differentiate with respect to the t prime, the source. Okay, so I'm using basically fx is so x0 is the root of this equation. Okay, that defines your t prime. okay, where this is 0. And so I'm using that formula to calculate this. Okay, and again, this has actually this trivial thing has a few steps. No, not this one. This one is direct, but after that, when you want to do this velocity, this is in the end it will turn out to be delta of okay, and the heart of all this, the result is, which I have not given, but it's a lot of algebra, so please look it up in the. So this is the standard thing for a linear Wishart potential. I mean, it's okay if you have seen this. So this is the derivation when you are calculating the scalar potential from a moving source. Okay, and you can get this. So now you can see that this is the time part has this non-trivial structure, and the space part for distance sources you can again write it as x and remove this. So in the end you can, when you integrate over time, what you are going to get is Hij Tx is 4g by r, where this comes from this part. This is r. So it's a distance source, but I am not neglecting the velocity now. Okay. So this T gamma n and okay. So this is your structure of your gravitational wave from a fast source. And notice, so here you will not see why you get a step function. You will just see that, okay, there is a constant which is depending upon the retarded time. Okay, something is moving. But notice, so what happens here is, let's say you have your ice cube neutrino which is traveling from a long distance, okay, and this will generate, if you write the T muni of that neutrino, okay, so if you're here, if you want to convert it into relativistic this thing, write the energy here. So for null fields, write Ni is the velocity of the field. So photon propagation is Ni, which is basically Vi by C. So it's only the direction. The velocities are only the directions, and this is the energy. So for null fields, what you get is Hij Tx is energy in a quanta, then n prime k n prime l divided by 1 minus n prime dot n. So n prime is the velocity of the field. So it basically depends upon, it's a unit vector, but depends upon the angles, the direction. Whereas, so this is the thing if you have a relativistic source. Okay. Okay, so as I was saying, if you have this kind of source, okay, you have a relativistic neutrino which is propagating, it does not emit any, I mean, the potential here is constant, okay, because there is no time dependence here. But if you have, supposing you have a supernova neutrino, then, so this is your t and x axis. Okay, so this is a neutrino propagating forever from free space, gives you a constant Hij which you can't observe. Whereas if you have a supernova neutrino, then you have a neutrino produced at some point. Okay. So what happens is that you have to multiply that with a theta of t retarded, let's say, where t retarded 0 is where it was 1. So then this gives you a step function. So this is for sources which are just produced, and so the examples of this is, okay, how much time do I have? I have not yet gone into the,
1.5 hours.
I have already done 1.5 hours. Okay, I'll just stop with this nonlinear this much, and I think I'll do this field theory, this, I have not connected it with the soft theorems. Okay, so what I'm going to do is actually connect these guys to soft theorem, which I'll do it next time. So I'll just give you that something called the nonlinear memory, which is actually, I mean, this is so I'll just do this very quickly. Or it's called Christodoulou. And this is important because this is the first memory signal which will probably be observed. So here the story is, as I said, you have a binary merger. Those are not relativistic, but they produce gravitons, okay, h mu nu, and these h mu nu act as sources for secondary gravitons. So primary, and this is secondary. Now you may think that, okay, if you have this secondary source, it will be suppressed because each coupling is suppressed by 1 power of g. Then you will have a g suppression here plus a g suppression there, so it will be not suppressed compared to the primary signal. But it turns out that actually there is a cancellation of this G suppression, which makes this a signal which is actually, I mean, something which can be observed. So to start with, so this is the stress tensor of gravitons, of h mu nu, I should write here. So what you do is, you write your metric, your Lagrangian to the third order in h mu nu, take del S upon del h mu nu, that is the t mu nu of the graviton, which is a bilinear object. And since this graviton Lagrangian is 1 by 16 pi g, and by taking the derivative you get a half t mu nu, so what you will get here is 1 by 32 pi g, okay, because this comes from the original Lagrangian where is a g in the denominator. And then this is del alpha h mu nu, and you take a time average over the oscillation time, so that you get a steady, stable non-oscillating part. You pick the non-oscillating part. Okay. So the message here is that, so the T00 here is the energy. Okay. So even a small amount, and here you have a M Planck square in the numerator. So a small gravitational signal, the strain, produces a large amount of, is associated with a large amount of energy released. So whenever you have a binary merger, the binding energy gets converted into gravitational waves. The strain is small, which we derived, is 4g by r, but the energy associated with this is large, and then that energy is the source of your secondary gravitons, which is why there is in the T mu nu itself, there is this at the denominator. So I think I'll just write the answer here, and it says, so if you use this T, then your Tij is minus Ni Nj T00, where this is the direction of the gravitons and this is the energy of the gravitons. This can be derived using the conservation of the gravitons test energy. Okay, and insert that in the this calculation, and what you end up with is what I had written, that for G okay, so this is the graviton and this is the source. So this comes by using this in this one kind of formula. So as I said, that your m omega gets replaced by this. Now I put a omega dependence because in general, whenever you have a binary, this is not uniformly radiated. It is radiated preference, that is angular dependence. So you have to take care of this angular dependence. That means you have a angular dependent integral still left. Okay. But the thing to notice is that this h, as we said, falls as 1 upon r square, right? But then you have a integral over d cube x. Sorry, h goes as 1 over r. So 2 h's, the h dot t00 will be h dot h dot. So omega square by r square. There is a, so this goes as omega square by r square. But this has to be integrated over the volume. So volume has a r prime square.
So what is the average over? Is it a time average?
Yeah, it is a time average. Time average over t greater than 1 by omega, where omega is the frequency. Okay. So in the d cube x prime, there was a r prime square. That cancels that r prime square over there. So there's a little bit, few steps, but you can look it up in some notes.
So essentially, this particular nonlinear term, if the term comes from the graviton side, you're treating as a source in the and then averaging all this, and then you're applying this formula, you get this.
Correct. Exactly. So I am using the T mu nu of the graviton, which. So even secondary gravitons are actually not suppressed compared to this, and this is something which will be seen. So the only suppression comes from these angular variables, angular integrals. So there is only one order smaller than the primary h mu nu signal, the memory signal, and that would be interesting too. So the memory signal, I have now spoken the whole time without. So normal signal will go like that. The memory signal will have some DC component. Okay. So that DC component is related to the fact that there is a time dependence in the source. The source starts at some point, I mean at the merger. Or a neutrino is emitted at some point. And okay, so that is all from the classical thing. And next I will do this, how this is related to this graviton theorems. So you'll see that actually if you use the soft graviton theorems, this is like a one line. You don't have to go through that much algebra to calculate things. Okay, so I'll stop here. Thank you. Huh?
We don't fight it, yeah.
Yeah, day after tomorrow. And you can borrow this notebook and take pictures if you are interested in the intermediate steps. But these are available in various textbooks and lecture notes and so on. So you can also see those.